Derivatives of logarithmic functions. Essential question. Can I take the derivative of a logarithmic function? The derivative rule goes like this. The derivative of log base a of x is equal to 1 over x times the natural log of a. In common terms, I just say 1 over the argument, 1 over the argument, and in the denominator times by the natural log of the base. Now, if you're working with natural log of x, then your base is e. So this will be 1 over the argument, natural log of e, and we know that the natural log of e is 1. So this will simplify to 1 over x. Now, how does that happen? Let's go ahead and take a log expression and rewrite it as an exponential expression. We're going to use the chain rule in this case. I'm going to take the derivative of this side, which is an exponential is itself times the natural log of a, but don't forget to use the chain rule, dy dx. The derivative of x is 1. We're going to solve for dy dx. That's going to be 1 over a to the y, natural log of a, and we can resubstitute and we can write a to the y as x. So that's why it works, and I've already talked about when you have base e. Okay, let's go ahead and utilize these. Natural log, it's 1 over the argument x cubed plus 1 times the derivative of the inner function, which is 3, which is going to be, I'm going ahead of myself. So we're going to take the derivative of x cubed plus 1, and so the answer is going to be, this should have been a prime, y prime is equal to 3x squared all over x cubed plus 1. So again, the natural log of a differentiable function is 1 over the argument times the derivative of the inner function, whether it's in u or it's in a function notation. Okay, let's go ahead and do this. Again, this is a natural log, 1 over the argument, sine of x. We're going to take the derivative of the argument, and our answer will be a cosine of x all over sine of x, and if you want to go one step further, cotangent of x. Here, the outer function is a square root, so I took the derivative of the outer function, and then I'm going to take the derivative of the inner function. This is going to be 1 over 2 root natural log of x times 1 over x. All right, here's a log base 10, and I'm going to write 1 over the argument, natural log of 10, and I want to take the derivative of the inner function. So that's going to be cosine of x all over the natural log of 10 times 2 plus sine of x. Now you can approach this in a different way by using a base change formula. So you can take this and write the base change formula right here, natural log of the argument divided by the natural log of 10. And I want you to notice that this part right here is a constant. I haven't done any calculus yet, but I'm about to. So I want to find the derivative, and this constant's not going to change, natural log of 10, but I will be taking the derivative of the natural log of 2 plus sine of x here. So the answer will be 1 over natural log of 10 times 1 over the argument 2 plus sine of x times the cosine of x. And I think you see it matches what I have over here. All right, here's derivative of a natural log expression, quite lengthy here. Notice that we're going to use the natural log rule, which is 1 over the argument, you see here, and then I've got to take the derivative of the argument, which is going to require the quotient rule. Notice that this is the quotient rule. When you clean it up, it looks something like this. Solution 2 is to simplify first. Before taking the derivative, take a look at this natural log and rewrite it into the difference of the natural logs. And also notice I use that exponent property where this was to the 1/2 power, and I brought it down as a coefficient. And now take the derivative of each one of these natural logs, and this should be the same, and a lot of people prefer this method. All right, I'd like to find the derivative of the natural log of the absolute value of x. This is the graph. It's actually a reflection over the y-axis. I'm going to rewrite it as a piecewise function and take the derivative of each one. Notice that we're going to get the same result. And the results are going to be quite interesting in that when x is greater than 0, the slope should be positive because I'm putting positive numbers here. And when x is less than 0, those are negative x values, and I should be getting a negative expression for the derivative. So that makes sense. Logarithmic differentiation. Here's a technique of differentiation. When we have a complex expression like this, we're going to require the quotient rule, the product rule, the chain rule. Consider doing logarithmic differentiation. I'm going to take the natural log of both sides. So this will be the natural log of y. And before I even start the calculus, I'm going to do some simplifying. I'm going to take the natural log of a quotient is the difference of the natural logs. The natural log of a product is the sum of the natural logs. Take all these exponents, make them coefficients, and once you're there, now take the derivative. So this will be 1 over y times, chain rule, y prime, equals, and then you just go ahead and start taking the derivative. 3/4 times 1 over x plus 1/2, 1 over the argument, times 2x, that's my chain rule, minus 5 times 1 over the argument, times the chain rule. And to isolate y prime, you're going to have to bring the y to the other side. And remember what y is equal to. Y is equal to this. So if you want everything in terms of x, that's what you would have to do. Okay, let's take a look at trying to differentiate this expression. It's neither an exponential nor a power. You have to use logarithmic differentiation. You have no choice in the matter. So we're going to take the natural log of y and the natural log of x to the root x. We're going to use our natural log properties here. The derivative here will be 1 over the argument, and here's the derivative. And you're going to use the product rule, and we're going to move the y to the other side, and then once we're going to resubstitute the y, and now this derivative is in terms of x. Consider another method, and here's the other method. Knowing that e and natural log are inverses of each other, you can take x and rewrite it this way, and that's exactly what's happening here. We're taking x and we're rewriting it. The reason we're doing this is so that we can get a base that's something other than x, because we know how to deal with an exponential with e. The derivative of an exponential e is itself, so you can see it's itself, and then you're going to use the chain rule and times by the derivative of the inner function, which is going to require the product rule. So here's the product rule being used, and remember this expression is just x to the root x. So this is a way to get to the same answer. Okay, the number e is a limit. All right, let's go ahead and write the definition of a derivative at 1. This is for any f, any function. I'm going to substitute the h's and I'm going to put x's in its place. So we still get the same expression. This using the variable h or using the variable x will yield the same results. Now I'm going to substitute the actual function natural log, and so this is going to be here and here. Now this is going to be 0, so this will be 1 over x times the natural log here. I'm going to use the natural log properties and make that an exponential. Continue on the next page. Remember that this is the derivative at 1 that I've been working with, so this expression came from a derivative and it's going to be equal to 1. Now I'm going to start here at e, and I'm going to build on the number e to the first, and then this is another name for the number 1, so this is going to be substituted. The limit expression is going to be brought outside the e, and so I have this. Now e and natural log are inverse functions, so I'm going to get this expression. And remember, this came from e, so this is very important. This is a limit that must be memorized. Now, in previous courses, we've just had you look at this expression getting closer and closer to 0 so that you can see that it equaled, that it was getting closer and closer to the number e, or we made you put it on a graph to convince you. Okay, so again, this is that double star limit that I expect you to memorize. Now, what I'd like to do now is I'd like to, we're going to let n equal to 1 over x, or x equal to 1 over n. They mean the same thing. So I'm going to take x. As x gets closer and closer to 0, as x gets closer, I should write x. As x gets closer to 0, that forces n to go to infinity. X is getting closer to 0 from the right-hand side, I should say. So this will be exchanged for n approaching infinity. And then I'm going to take this x and replace it with 1 over n. And again, I'm going to take 1 over x and replace it with n right here. And so this is another double star limit that you're going to need to memorize. So as n approaches infinity, 1 plus 1 over n to the n is equal to e. And I think we did this with you in pre-calculus with compound interest, where the number of times that it's compounding is going to infinity. So this should look a little familiar. And this is the end of the screencast.